So today we can look at the nature of radioactive decay. Remember that radioactive decay is spontaneous, and the key thing is it's random. When you listen to the Geiger counter, when you've got a radioactive source near it, it's not clicking at a regular count. You can clearly hear the randomness in it. But what does this mean? Well, the OCR definition is this. Spontaneous means that decay cannot be induced or it occurs without external influence, which means it can't be influenced by pressure, temperature, anything like that at all. So we've got no control over the rate of decay. Secondly, it's random because we can't predict when or which nucleus will decay next. So using dice is a great way of modelling radioactive decay. First of all, it's random. You can't predict when a dice will land 6 upwards, or which dice, if you've got a whole sample of them, will land 6 upwards. And of course it's spontaneous. We have no influence over this decay at all by external factors. So what we're going to do now is look at practical results from 2 groups that I've collated and see what we can learn from it. So to do this experiment, each student starts with 80 dice in a beaker. They shake the dice and then throw them into a tray. The ones that land 6 upwards we say have decayed and are removed from the sample. The students then put the undecayed dice back into the beaker, shake the beaker again and throw the dice out, and keep repeating the process until about 10 throws have taken place. So I've collated 2 class sets of data which were saved on my computer, and you can see that that gives us 20 groups in all, which is 1,600 dice in total. And the more dice you have in your sample, the more accurately it models radioactive decay, because of course a sample of radioactive material will contain trillions and trillions of nuclei, not just 1,600. You will notice as well, pausing the video, that the data is completely random going down each of the groups. And out of this total randomness comes the most beautiful decay curve, as you can see. Now, radioactive decay is an exponential function, which means that it drops by the same factor in the same time interval. So let's first start by measuring how many throws it takes to get rid of half our dice. As you can see, it takes 3.8 throws to get rid of exactly half the dice. So let's see how long it takes to get rid of half again. So that's 400, and if you have a look, it takes another 3.8 throws to get rid of half again. Finally, we can see it takes another 3.8 throws to drop again by a half from 400 to 200. So every 3.8 throws it drops by the same factor of 2. This is the key trend of exponential decay. The variable drops by the same factor in the same time interval. So let's look at the maths behind simulating radioactive decay with dice. So why are dice a really good model of radioactive decay? Firstly, it's random. We can't predict which dice, acting as nuclei, in the sample will decay next. Also, each dice has the same chance of decaying per throw, which is a 1/6 in this case. Also, it's spontaneous. The decay cannot be affected by any external factors. So let's look at the mathematical theory behind probability. Well, the probability of the dice landing with a 6 side up is a 1/6, which means the probability of the dice not decaying is 5/6. So how can we work out how many dice will be left after a certain number of throws? So for one throw there's 5/6 chance that they won't decay, so the number left will be 5/6 of n0, the original sample number. For 2 throws it will be 5/6 of what's left, which is n0 times 5/6. At 3 throws it will be 5/6 of what was left after 2 throws. So we can write a general equation that after t throws the amount left will be n0 times by 5/6 to the power t. The half-life of the dice is how many throws it would take to get rid of half your dice. So how can we work this out using the above equation? So the above equation will equal a half of what was there originally when the number of throws is the half-life. We can take out n0, the original number of dice, from the equation. Now we can take logs to the base 10. Remember, log a to the x is x log a. So taking logs of the above equation, we get t to the half log 5 over 6 is equal to the log of 0.5. This gives the number of throws to get rid of half the dice, t to the half, equal to log of 0.5 divided by the log of 5 over 6, which is equal to 3.8 throws. So let's compare this with the practical results from our dice throw. As you can see, the theory matches the practical because we found out we got 3.8 throws to get rid of half the dice. From the original data we got, I can also plot activity against the number of dice. The activity in the model is just the total number of dice removed each throw from the class. It would seem logical that the less dice left in your sample, the less is going to decay in that throw. So there should be a linear relationship between them. As you can see, plotting the activity, the number of dice discarded per throw, against the number of dice in the sample, you can see that they are directly proportional within experimental error. We can also use Excel to add an equation to this to see the value of the gradient, the constant. So the equation for the straight line gives a gradient of 0.18 and an intercept nearly 0. Rewriting that with activity and number of dice gives us a constant of 0.18, so we can say that A is directly proportional to N. So if I get Excel to plot activity against number of throws, it should have exactly the same curve as the number of dice left against throws, because they're directly proportional. Notice because our sample is not that large, the number of throws needed to reduce the activity by half each time is just very slightly less, but nearly matches the other graph. Before we move on to the mathematics of exponential functions, let's have a look at how we can work out activity more accurately using the original graph of number of dice left against number of throws. So activity is the rate at which the number of nuclei decay each throw, which is actually the gradient of the graph. Let's start by measuring the activity when there are 800 dice left in the sample. The best way to draw a tangent to the curve is first draw a line at right angles to the curve. This apparently is easier to gauge than going and doing the tangent straight away. You can now easily draw a line at right angles to this, which is the tangent to the curve. So the activity at 800 dice is equal to delta n over delta t. Each square on the y-axis is worth 40. So that gives a value for delta n as 1368 roughly. Divided by delta t, which is 8.8, gives us 155 as the activity. Now if I do the same thing by working out the activity when there are only 400 dice left in the sample, we get the following. Finally, does the activity calculated this way using the gradient match with the activity we got on the Excel spreadsheet by plotting the number of dice removed in each throw? From our gradient, the activity at 400 dice was 76. If you look at the Excel spreadsheet, 400, it works out to be 75, very close. The activity at 800 dice in the graph was 155. From the Excel spreadsheet, you get roughly 150, which roughly matches 155 within an experimental error. So the activity, the number of dice decaying every throw, is equal to delta n over delta t, which is directly proportional to the number of dice in the sample. This shows a really important fact about exponential growth or decay, that exponential growth or decay occurs when the rate of change, that's delta n over delta t, of something is directly proportional to the thing itself, which in this case is n. This key aspect of exponential growth or decay can be written as delta n over delta t is proportional to n. We can write activity is equal to minus kn, where k is the constant of proportionality. The negative sign shows it's decay, not growth, but we don't ever use the minus sign in calculations. Before we look at logs to the base e, it's important to remind ourselves about what logs to the base 10 and logs to the base e mean. So what does log to the base 10 actually mean? Well, let's use the example of 10 to the 3. What does it equal? You'll see on your calculator, if you look at the log function, you can see the inverse of the log function is 10 to the x. This is equal to 1000. So the log of 10 to the 3 should just be the power, which is 3. So you can see that log to the 1000 is just 3. So what about logs to the base e? When taking logs to the base e, we give the symbol ln, so not to confuse it with log, which is logs to the base 10, rather than log to the base e. So what is the value of e? Well, we can work that out by doing e to the power of 1. You can find e to the x on the inverse, the shift of the ln button. So e to the 1 is just equal to 2.72. So for example, e to the 3 would be equal to 20.1. Sorry, I've written 20.0. Similarly, 2.72 to the power 3, which is e to the 3, should give us the same number. So the log of e to the 3 should just give us the power, which is 3. So the log of 20.0 does give us 3. Hopefully this gives you a reasonable idea of the difference between logs to the base 10 and logs to the base e. There are many examples in nature where things decay or grow exponentially. So let's now look at other graph results in more detail and more mathematical modelling of exponential decay. Just as a reminder, plotting a graph of activity against the number of dice gave us a directly proportional relationship. So activity was proportional to n, so A is equal to Kn, where K is the gradient of the graph, which was 0.18 for our dice experiment. So the constant of proportionality for the relationship is 0.18. Because activity is directly proportional to the number of throws, then if we plot the activity against the number of throws, we get exactly the same relationship. After having a brief look at logs to the base e, we can now think about what the basic equation is for exponential decay. The basic relationship for exponential decay is n equals n naught e to the minus kt. So what do each of these symbols mean? N stands for the total number of dice left after a certain number of throws t. N naught is the initial number of dice you start with, which in our case was 1600. The fraction left after a certain number of throws is governed by the exponential decay e. The negative shows its exponential decay. If it's a positive, it means exponential growth. K is the decay constant, which controls the rate at which the factor decays against t. The constant depends on the probability of decay. In our case, it was 1 in 6. We can see in the graph above that plotting n against t gives us a curved relationship. So how can we get a linear relationship? Well, we need to take logs to the base e, where the log of e to the x is just equal to the power x. So n is equal to n naught e to the minus kt. So taking logs to the base e, we have ln is equal to, don't forget when taking logs, if two things are multiplied together, you can split them up. So it's the log of n naught plus the log of e to the minus kt, which gives us the log of n is equal to the log of n naught minus kt. So we can rearrange this in the form y equals mx plus c. Where c is a constant equal to log of n naught. The gradient m is minus k, the decay constant. X is equal to the variable t, the number of throws. And y is the log of n, the number of radioactive dice left. So what do we get with our actual results from the class set if we plot log n against t? Plotting the actual data using Excel, you can see that we've got a linear relationship of log n against number of throws. Adding an equation to the trend line gives us the following. Changing y for log n and x for t, we have the following equation. The decay constant, the gradient, is 0.18 and the intercept of the y-axis is 7.37. So adding the graph of log n against t, the number of throws, to our notes, we can see that it's a linear function, where the gradient is the decay constant. Our experiment gave us the equation the log of n is equal to minus 0.18t plus 7.37, where 0.81 is the decay constant, and the log of n0, the intercept with the y-axis, is 7.37. If we do the inverse log of 7.37, that gives us n0, which is roughly 1,590. This is very close to the 1,600, which was the dice that we started. This was our n0. Finally, if you look at the decay constant value we got by taking logs, it was 0.18. If you have a look at the gradient for activity against dice, which is also the decay constant, we also get 0.18. I love physics. Sometimes the maths in it is just beautiful. Believe it or not, there's even another way of finding the decay constant using our original graph, where we got the half-life of 3.6 throws. So when the number of throws is 3.8, then we have only half the number of dice left. So the number of dice now divided by the original number of dice is 0.5. Knowing exponential decay, we have n equals n0 e to the minus k t to the half, where t to the half is the number of throws needed to get rid of half the dice, which is 3.8. Dividing through by n0 gives us n over n0 is equal to e to the minus k t to the half. Don't forget, a negative power is actually an inverse relationship. So e to the minus k t to the half is actually equal to 1 over e k t to the half. This means we can get rid of the negative sign by inverting both sides of the equation above. Now n over n0 will be equal to 0.5, which means if we invert that, that gives us a value of 2. So taking logs of both sides of the equation gives us the following. This can be simplified to k t to the half is equal to the log of 2. Dividing by t to the half gives us the following. T to the half, the number of throws needed to get rid of half the dice, is 3.8. So this gives us a value of k equal to 0.18, the same as before. Magic. So to just summarise and recap the key details. We started by plotting the number of dice left against number of throws, and we got an exponential decay curve. We proved it was exponential because it dropped by the same factor of 2 in the same interval, which was 3.8 throws. We then plotted activity, the number of dice decaying every throw, against the number of dice in the sample, and we showed that they were directly proportional. So A was equal to Kn, where K was the decay constant, which for us was 0.18. Because activity was directly proportional to N, plotting a graph of activity against number of throws gave us exactly the same results, showing it was also an exponential curve. We then quoted the general equation for exponential decay, n equals n0 e to the minus kt. We then took logs to the base e in order to get a linear relationship with the form y equals mx plus c. Plotting a graph of log n against the number of throws gave us our linear relationship. The gradient gave us minus the decay constant, and the intercept of the y-axis was the log of n0. So inversing this would give us the original number of dice in the sample. Similarly, plotting a graph of log of activity against t gives us the identical relationship. The last equation we proved was for the decay constant k, and k is equal to the log of 2 over t to the half. That sums up all the equations that you need to know. The last thing I want to do with you is look at our model of dice to see how probability affects the decay constant. So supposing this time we said that the dice decayed if a 3 or a 6 landed up, then the probability of the dice decaying would be 1 in 3. So the probability of the dice not decaying would be 2 over 3. So what is t to the half, the number of throws needed to get rid of half the dice? Remember, n0 times the probability of not decaying to the power of the number of throws, if it's the half-life, will allow you to have 0.5 of what you originally had. So eliminating n0 gives us 2/3 to the power of t to the half is equal to 0.5. Taking logs to the base 10, we get the following. This gives us t to the half is the log of 0.5 divided by the log of 2/3, which equals 1.7 throws. Finally, the decay constant k equals log 2 divided by t to the half, which is log 2 divided by 1.7, which gives us 0.41, which is a much larger decay constant than 0.18, so it will decay much more rapidly. In the next video, we'll look at how we apply these type of equations to radioactive decay, including using Avogadro's constant to work out the number of particles in a sample.